Good morning. This is the last video on chapter 5, and we're talking about independence, talking about two events that are independent. Let me remind you before I tell you what independent events are that you have to keep that separate from two events that are mutually exclusive. Remember that the phrase or the term mutually exclusive and disjoint are interchangeable, and two events are mutually exclusive if they both can't happen, which in formula speak would be if they're mutually exclusive, then the overlap would be zero. The probability of A and B would be zero if they both can't happen. So that's mutually exclusive. And it's easy to confuse independent with mutually exclusive. So keep in mind what mutual exclusive events are. They both can't happen. Independent events are different. So here is the official definition of independent events. It says two events are independent if the occurrence of one event does not change the probability that the other event will happen. And that word independence kind of makes sense. They're independent, so the probability of this event happening does not depend on whether the other event happened. So, can they both happen? Sure, they can. But if you know one of them happened, then it does not change the probability that the next one will happen. That's what it means for two events to be independent. So here's a simple example where I think hopefully, obviously, the events are independent. My example here is I toss one coin and I roll one die. And let's call event A that I toss a heads and event B that I roll a 5. I think you would agree with me that those two events are independent. Like when I roll that die, the probability of getting a 5 does not change if I tossed the coin earlier and got heads or didn't get heads. Like knowing one happened does not change the probability of the other. So there's an obvious example of two events that are independent. And sometimes, just given the context, you'll have to be able to identify that they are in fact independent. Sometimes you'll have to do some math to figure out, and we'll get to that math. So now let's look at the question at the bottom. It says, what's the probability of A and B? Like, what is the probability that they both happen? Well, I don't think it should surprise us that first, if I toss the coin, the probability that I get a heads is in fact 1/2. And then I also need to roll a 5. And the probability of rolling a 5 is 1 and a 6. I in fact am going to multiply those. Just 1/2 times 1/6, which is what 1/12. Now, I mentioned yesterday how helpful a tree diagram could be. I don't know that I need one here, but I want you to see that it would help. Let's say I first toss a coin. I either get heads or tails. And then I roll a die. Now, I could break that into 6 outcomes, but since I'm specifically looking for rolling a 5, let's say I roll a 5 here and not a 5 there, and a 5 there and not a 5 there. So let's label some probabilities. My heads and tails are both clearly 1/2 and 1/2. And then whether I tossed a head or a tails, the probability of rolling a 5 would be what, 1/6, and that says 1/6, and not would be 5/6, and then down here would be 1/6 and 5/6. And I have 4 outcomes here, right? I have heads 5, heads not 5, tails 5, tails not 5. I could multiply all the probabilities to find the probability of each outcome. In particular, if I want A and B, I want heads and roll to 5. That happens to be asking for that particular path, and the probability of that path, just like yesterday, multiply the probabilities along the way. Excuse me. So it'll be 1/2 times 1/6. So in general, the conclusion here is that if the events are independent and you're trying to find the overlap, you could just multiply the individual probabilities. Remember yesterday, we talked about what state it came from and laptop, and like the probability of a laptop was different for each state. So I had those probabilities weren't the same for laptop or desktop because it mattered what state you were in. But for this one, tossing a coin and rolling a die don't affect each other's probabilities at all. So I can just multiply the probability. So 2 important conclusions here. Here's the first one. We kind of just said it. And please know that this sentence, I wrote it both directions, and you may be asked to use it in both directions. The first sentence says, if the events are independent, then the probability of A and B equals P of A times P of B. If you know they're independent and you're trying to find the overlap, you can just multiply P of A times P of B. The second statement here says, if the overlap is in fact P of A times P of B, then you can conclude that they are independent. And that will certainly happen sometimes. The question will be, hey, here's a scenario, here's some events. Are these two events independent? Like yes or no, you have to figure it out. One way to do that would be just to check this math. If the overlap is P of A times P of B, then yes, you can conclude they're independent. Or it could go the other direction. Like I said, the problem might say A and B are independent. Then if you're asked to find the overlap, then you need to know just to multiply them. So these two sentences on this page, it's the same conclusion, kind of the if and then the then are switched, and it could work in either direction, depending on what information you're given and what information you are asked. Okay, so that's the first important conclusion about independent events. And I suppose the first conclusion was keeping track of how they're different from mutually exclusive events. The second conclusion is this, that if they are independent, I can just multiply the probabilities. So for instance, what's the probability that I toss a coin 7 times and get a head 7 times? Each time I toss the coin, those are independent. The probability of one particular heads or tails does not depend on what happened to the last coins. So I wanted to toss 7 heads in a row. It would be 1/2 times 1/2 times 1/2, 7 times, or 1/2 to the 7th power. That's an example of multiplying events because they're independent. Excuse me. All right, last thing. Oh no, I lied. Is a good example of whether they're independent or not. So, and this is a very kind of classic example. Bag has 6 red marbles and, ooh, I can't spell. It says 3 blue marbles. Let's call that blue. 3 blue marbles. 2 marbles are chosen with replacement. Find the probability that both are red. That with replacement is vital. That's why I made it bold. That means I pick one, and then I put that marble back. I replace it in the bag, shake the bag. I'm going to pick another one. And because I replaced my first marble in the bag, the probability of getting a red marble does not change the second time around. If my first marble were out of the bag and not replaced, it absolutely would change. So you need to recognize that these two events, the first marble I choose and the second marble I choose, are in fact independent. So I can just multiply the two probabilities. The first time I go into that bag, the probability that I get a red marble is what? Let's see, there's 9 marbles total. 6 of them are red. That would be 6 out of 9. And I can reduce that. We'll take this out in a minute. And then the second marble, because I replaced it, the probability of red the second time around has not changed. So it would be times 6 out of 9. And if I did that, that'd be 36 out of 81, which I think is 4/9. So I could multiply the individual probabilities because they were independent. Okay. And again, I could have made a tree diagram. I got red and blue, and I got red and blue, red and blue. Probably if red would be 6/9 times 6/9. Now, maybe more important, let's talk about what happens if I do that without replacement. That means I picked the first marble. There were 9 marbles in the bag at first. I picked the first marble. I want to get a red one the first time. When I go back to choose the second marble, the one I chose, I have not replaced, so the probabilities are different. So it's not 6/9 times 6/9. And I'm going to do this 2 ways. I'm going to make a tree diagram. First is either red or blue, and the second is either red or blue or red or blue. The first marble I choose, probably of red was 6/9, probably of blue was 3/9. But what about my probabilities? There are my lights. What about the probabilities for these other two? They're going to change. They're going to depend on what happened the first time. So let's look at the top here. I'll do this in blue. I'm trying to put a number right by this blue line right there. So the second time I go into the bag to choose a red one, well, I chose a red one the first time of that one. My first one was red, which means there's only 5 red left, and there's only 8 total left. And then similarly, if the first one was red, I still have the other 3 out of the 8 were blue. What about down the bottom? I'll do in green. What if I want to do this one here? What if I pick blue first and then red? Well, blue was 3 ninths. I picked the blue one, so there's 1 less blue ones, and then there's only 2 blue ones. There are still 6 out of the 8 left there are red, and the other 2 are blue. So, and that looks a lot like the tree diagram we made yesterday. So, now this is a little bit of overkill because if all this particular question wanted was red and red, I really just need this path right here. Like that's the red path. So the probability of red and red would be the first one red, which is 6 ninths, times the second one red, which is no longer 6 ninths. It is now 5/8, which equals whatever it equals, 30 out of 72. I can divide that by 6, I guess. I don't know, 5/12 maybe. 3/4 divided by 6. I think so. 3/4, 1/3. Yep, 5/12. Okay, so that example, they were not independent because the probability changed after I chose the first marble. The one before they were independent. So if they're independent, you can just multiply the 2 probabilities. And if not, like this, you just have to figure out what the second probability is. You're still multiplying probabilities, but the probabilities change because of the dependence. All right. Now for the last topic in this section. Now, what about conditional probability? What if I want A given B? So let's think about this. You know the formula. The probability for A given B is the overlap over the second. Like that formula is fine and it always works. But if 2 events are independent, let's go back to my let's go back to my first example. Let's say A is I toss a coin, I get heads, and B is I roll a die and I roll a 5. So this one right here, A given B, that says what's the probability that I toss heads given the fact that I rolled a 5? Well, what's up with that? I'm given the fact that I rolled a 5. What you need to figure out is, in this case, that does not change the probability at all. The probability that I toss a heads is the same whether I rolled a 5 or not. So it's A given B, but if they are independent, remember the definition of independent means that if I know something happened, it doesn't change the probability. So the probability of A given B is like that, given the fact that I rolled a 5 doesn't matter. It is in fact just 1/2, which is just the probability of heads. And then what if I go backwards? What's the probability that I roll a 5 given the fact that I tossed heads on my coin? Well, who cares if I tossed heads on my coin? That doesn't change the probability. That's still just 1/6. So the conclusion is if they're independent, the temptation here is to forget the formula, which says the probability of A given B equals the overlap over the second one. That formula is correct. And if you're not sure they're independent, you better use that formula. But if they are independent, then the thing that you're given doesn't matter. So the conclusion is this. And again, you'll notice that this works in both directions again. And what I mean by that is either you'll be told they're independent and be able to conclude something, or you'll see something's true about some probabilities and then conclude that they're independent. So the first half says if they're independent, then the probability of, I'm looking at this one right here, then if we know they're independent, then the probability of A given B equals the probability of A. Like the probability of A doesn't change given the fact that B have it because they're independent. Or I could switch it in the second line here. The probability of B given A, if we know they're independent, is just going to be the probability of B. So again, sometimes you'll be told 2 events are independent, and if it says, what's the probability of A given B, you have to know, oh, that's just the probability of A. You can't assume it if you don't know they're independent, but sometimes you're told the 2 events are independent. And at the bottom here, it works in the other direction. You might have a bunch of probabilities. P of A is this, P of A and B is this, P of A given B equals this. Like you might have numbers for those. And the question will say, are events A and B independent? And again, another typo here, sorry. So if the probability of A given B equals the probability of A, so like if it turns out that equation is true, then you can conclude that the events are independent. So formula-wise, two things going on with independence. If they're independent, then P of A and B equals P of A times P of B. And if they're independent, then the probability of A given B equals the probability of A. And then I can say both of those backwards. If the probability of A and B equals P of A times P of B, then they're independent. Or like the bottom here, if the probability of A given B equals the probability of A, then they are independent. So it kind of works in both directions. Okay, so it's more confusing than it is difficult to just make sure you read the question carefully and understand what's going on here. So last thing here, the assignment for this section is on page 336. Page 336. And you're doing just a number of these. You're doing 83 to 94, which are just some regular questions. And then like most sections, I have a few for multiple choice questions, 97 to 99. Just looking ahead, I think the test is going to be Wednesday. We have a live lesson. I think during that live lesson, we'll do some sort of review, and then I will post the test. So I will give you a full-fledged test review on Monday, which we will then answer key posted on Tuesday. Wednesday, we'll do a review in class in the morning, and then I will post the test. And then Thursday, we'll start chapter 6. So that is the plan. Have a great, and again, I do look kind of foolish here. Got my tie on and Morpy, and so enjoy Morp Day.